Welcome back. This is my first video on Chapter 8, which covers ARIMA models. So what is an ARIMA model? Well, ARIMA model I think of as an alternative to the ETS exponential smoothing models that we covered in the previous chapter. Both of these approaches really offer a family of models that are capable of describing a wide variety of time series data, and they're both among some of the best forecasting methods out there. The thing is, they follow a different approach. So ETS really focused on how do we capture the trend, and so the Holt method allowed us a way to have that trend evolve over time, and seasonality. So the winters part of Holt winters adds the seasonal part. ARIMA is going to focus on something completely different. So instead of focusing on the trend and seasonality, ARIMA is going to focus on the autocorrelations between observations in the time series. I want to start with some notation and terms. The first is ARMA. So ARMA, the I is missing from there, and that's not a typo. ARMA stands for autoregressive moving average. We're going to have a series of models. Now remember, I just said ARIMA focuses on autocorrelations. The way we're going to deal with the autocorrelations is in basically two ways. So the autoregressive part is I'm going to fit a regression predicting y sub t using the previous observations. So in the simplest case, I would have y sub t as a function of y sub t minus 1. I'll just go over the document camera for a second. We're going to write this as this. Y sub t is equal to some, you can think of it as a regression like this, plus some errors. All right, so that's what autoregression is. We're going to regress y sub t on the previous value of y. Okay, the moving average part is going to be to predict y sub t from previous errors, so from previous values of the residual, where that residual is saying are the points above or below the line if this were a regression line. So what the way I like to think about this is if we have cyclical behavior, let's say that we're in a booming economy right now, then 1yt would be above the line, so things are better than we would expect because of the booming economy. And because one value is above it, the next one's more likely to be above it as well. And so that's why that's the basic intuition behind a moving average. Likewise, if we're in a recession, then the values may be systematically below the line. And so one value being below the line suggests that maybe the next value and the previous value are also going to be below the line. And that's the intuition behind a moving average. Now, I find this slightly confusing, but the use of the term moving average in Chapter 8 is different from the use of the term moving average in Chapters 6 and 7. So this is not the ETS moving average where we just average subsequent observations. This means we're predicting y sub t from previous errors. ARMA is what we're going to be using to understand the autocorrelations and model the autocorrelations. These ARMA models are going to assume that our time series is stationary. So more on stationary in a minute. We talked quite a bit about this back in week 1. What are we going to do if we don't have stationary data? Okay, so what if we have a trend? What if we have seasonality? What if we have heteroscedasticity? The answer to those questions is that we're going to use Box-Cox transformations to stabilize the variance, and we'll take differences to stabilize the mean. We saw back in week 1 how differencing can get rid of a trend. We also talked about seasonal differencing back in week 1, where that took out seasonal components of the time series. So we're going to use differencing to avoid these problems. This gives rise then to ARIMA. So what does ARIMA stand for? Well, it's autoregressive, integrated moving averages. So now we have the I in there. What do we mean by an integrated process? So what we mean by that is we're simply going to compute differences. So we may compute first order differences as we did back in week 1. Maybe we do seasonal differences as we talked about in week 1. We may even do both. So more on that later in this lecture. The purpose of this, again, is to address trends in seasonality. Then once we've done that, we'll use ARIMA to deal with the autocorrelations. This video is going to focus on stationarity and differences as well. Then in the next video, we're going to talk about autoregressive models. Video after that is going to be moving average models. Then we'll combine all of the things and then finally get into ARIMA models for seasonal data. So that's where we're going. What is stationarity? So let me start by reminding you that the reason we care about stationarity is ARIMA models assume it. So we can't use ARIMA unless we've got stationary data. So what is stationarity? Well, this was the definition I gave you back in week 1. A process is going to be stationary if, for any window length S, the distribution of y sub t through y sub t plus s, so the next s observations, think of this as a window, doesn't depend on t. So this chunk of observations doesn't, the distribution doesn't change over time. That's the way to think about it. Here are some characteristics of stationary processes. So they tend to be roughly horizontal, so we're not allowed to have trends at this point. They should have constant variance. So back in week 1, we talked about how a random walk didn't have constant variance, and that was a violation of stationarity. Well, we've got to have that. Third, there's no predictable long-term patterns. And so really what I mean by this is seasonality. So if I know that every December my sales go up, that's a predictable long-term pattern. So stationarity is when you have none of these issues to worry about. Well, how do we diagnose whether our time series is stationary or not? We're going to use a lot of the tools that we've already seen before, but maybe with a new eye to identifying stationarity. So we're going to start with just the time plot. So plot yt versus t. We're going to look at our autocorrelation function. Remember, the autocorrelation function tells us the correlation between adjacent observations. So whenever we have stationary data, the ACF tends to drop off pretty quickly. Not immediately, but it tends to drop off fairly quickly. When you have non-stationary data, the autocorrelation decreases slowly, and often you have a very strong first autocorrelation value. So the first R1, so correlation between adjacent pairs of observations, would be large and positive, typically. We're going to have another diagnostic this video, which are called unit root tests. So one of these is going to be the KPSS test, and we'll also study the Dickey-Fuller test in this video. So let me just kind of recap the big process. If we detect non-stationarity, what do? Well, what we're going to do is use Box-Cox to avoid non-constant variance, and then we'll do various differences to address trends and seasonality. Finally, once we've removed the non-stationarity, then we'll go to ARIMA. So that's a summary of where we're going. We've talked about autocorrelations. I'll review those in a second. The only thing that's new is the unit root test. So your textbook really mentions one, the KPSS test. A second one that is a real classic, and therefore I feel like I'm going to just mention it, is the Dickey-Fuller test, or the augmented Dickey-Fuller test. The difference between these is in the null hypothesis and the way the test statistics are computed, but they both allow us to do the same thing. And so we want to know, is the data stationary or not? With KPSS, the null hypothesis is that you've got stationary data. So large p-values mean you can't reject that null hypothesis. Small p-values indicate that hypothesis is in question. With the augmented Dickey-Fuller test, it's just the opposite. So our null hypothesis is that we have non-stationary data, and the alternative is that we have stationary data. Let's go through a very simple example. We're going to go through all four of these diagnostics. You've got my code here, but I think it might be better to do it live. I did not put all the library calls in, but make sure you've loaded all of these libraries before you do anything. Let's go back to a data set we used in week 1, which was the Google stock price data. And so if I make a time plot, we see that stationarity is very much in question. The most obvious violation is the trend. So there's a very steady increasing trend here, which would signal that we don't have a stationary process. There may be some other things going on. The seasonality is hard to assess with this plot, and chances are there may not be any seasonality. Go back to week 1, we had some further diagnostic plots for helping us diagnose whether there's seasonality. Well, let's go look at our ACF. So remember what I said with the ACF. ACFs that drop off quickly are signals that you've got stationary data. This does not drop off quickly. Values between the blue lines are not significantly different from 0. First order, second order, all the way up to the 30th order, that's all we've shown here, are extremely big and positive, signaling we don't have stationary data. We've got a problem. That's largely due to the trend. Let's go look at the KPSS test. So as a little review, the null hypothesis is that you've got stationary data. When we look at the output, the value of our test statistic is over 10. Let's call it 11. They're giving us critical values for this test statistic. And so values of the test statistic that are greater than 0.7 would be significant at the 0.01 level. Let me repeat that. If our test statistic exceeds the critical value, we would reject the null hypothesis of stationarity. This test statistic is far beyond the 0.74. Why don't we just go write it here? So 11 or 10.7 is much, much greater than 0.7. So reject H0 data stationary. So this is telling us we have non-stationary data. That is our conclusion. We've got a non-stationary time series. Well, let's go run the augmented Dickey-Fuller test. The null hypothesis with this is non-stationary, and notice the p-value is large, so 0.349. So if we want to go write this out, p equal to 0.349 is greater than, say, 5% or 1%. We use the 1% cutoff since I used that up here. This is telling us do not reject H naught non-stationary. So I cannot reject the null hypothesis. Therefore, I would conclude that I probably have some stationarity going. All of these four diagnostics are telling us the same thing. This Google data is not stationary. Well, remember what we did to address non-stationary data before. We took differences. Now I'm going to compute the difference of the Google data. And what I see is just a random scatter plot here. There are no patterns over time. Earlier we called this a white noise process, so there's nothing going on. All indications right now are that this is a stationary data set. But let's go look at our other diagnostics. Remember, if the ACF falls off quickly, so let's go remind ourselves what we're looking for here. The ACF is dropping off quickly. What this is signaling to me is we don't have stationarity. Maybe there's a couple values that are just outside the blue lines, but those could just be false positives. I'm not going to worry too much because they're barely outside the blue lines. Let's go look at our KPSS test. So remember, the KPSS test has a null hypothesis of stationarity. And our test statistic is 0.03, which is way less than any of my critical values. And that's signaling to me that I cannot reject the null hypothesis of stationarity. So by differencing, we've avoided the problem of stationarity. If I do the Dickey-Fuller test, what we find is the p-value is tiny. I reject the null hypothesis of non-stationarity and go with the alternative that I have stationary data. I'd now like to walk us through a number of other data sets that we've been studying in this class and just see what's happening with them. So the first is the shampoo data set. So let's go take a look at the shampoo data. What I immediately see with this is, again, a very steady trend, steady increasing trend. This is signaling to me we don't have a stationary data set. If I look at the ACF, what we see is the first autocorrelation coefficient is pretty large. It falls off fairly slowly. So this is all signaling to me we don't have a stationary data set. If we go do the KPSS test, remember the null hypothesis is that you've got stationary data. The value of my test statistic is 0.9, which is greater than any of these critical values, suggesting that I would reject the null hypothesis of stationarity and conclude that this is non-stationary. The other test that we have is the ADG, or augmented Dickey-Fuller test. The null hypothesis is non-stationary here. We can't reject that null hypothesis because the p-value is very large, and they've all told us the same thing. Let's go look at the T-bill data. T-bill data, I would suspect this to be stationary because I would expect in the long term Treasury bill rates to hover around some fixed mean. So I think that makes this data set kind of interesting. However, given the time frame that I have from 1980 to 2010, there was a steady decline. Now, of course, the rate isn't going to go below zero, but at some point this is going to go back up. But maybe because of the window that I have, we may see a trend that we need to worry about. Let's go look at the ACF. The ACF is suggesting non-stationary. Our first autocorrelation is pretty big. Next couple are significant. So the next four are also significant, next five even. If I go look at the KPSS test, what we see is, I'm going to call this a borderline significant result. The reason I call it borderline is our test statistic is 0.6, which is bigger than some of these smaller cutoffs, but not bigger than the 1% cutoff. So we have somewhat of a borderline result, borderline significant result. So I'm I've got some indication this is non-stationary, but it really might be stationary. That could just be a false positive. Likewise, the Dickey-Fuller test, well, Dickey-Fuller is, we're nowhere near rejecting the null hypothesis. So we cannot say this is stationary using the ADG test. Now, if we were to compute differences on the T-bill data, I'm seeing something that looks much more like a white noise process. The variance is constant, there's no trend, there's no obvious seasonality. My ACF is all between the blue lines, so there are no large autocorrelations. We can see that with the KPSS test, we're nowhere near rejecting this even at the 0.1 level. And if we use the ADG test, we can easily reject the null hypothesis of non-stationarity, and therefore we would conclude the differenced data is now stationary. I want to show you a very interesting data set that is from the textbook. We haven't done much with it. This is the lynx, it's a type of cat trapping, and this is a very unusual data set. What happens is when the cats exhaust their food supply, they don't reproduce anymore. The population falls dramatically, then they start to reproduce again, and then at some point it falls off again. And so you see a lot of very strong spikes, but what's important to note is they're not at any regular frequency. So it's not like this happens every 3 years. Sometimes it's longer, sometimes it's shorter, probably depending on other factors like how much rain and sunshine there was. We look at the ACF, we see a lot of significant autocorrelations. So initially, they're very correlated with each other, then they're negatively correlated. So if we look at the current period and 5 periods back, they tend to go in opposite directions. So here we have a very strong ACF. If we look at our KPSS test, though, this is nowhere near being significant. That value is much smaller than any of the critical values, suggesting I can't reject the null hypothesis of stationarity. If we do the ADG test, we're going to come to the same conclusion. So tiny p-value means we're going to reject the null and conclude that it's stationary. So the reason this is stationary is because there's no trend, there's no non-constant variance, and there's no regular seasonality in this, even though it sure looks like a very unusual plot. But just a kind of a famous example of a stationary data set that doesn't look like it is at first glance. Well, let's go look at the Amazon data that we've analyzed to death in this class. So we've already seen this a million times. We have exponential growth with strong seasonal patterns, variance increasing. ACF is saying it's not stationary. We can reject the null hypothesis of stationarity because that 1.55 is much larger than any of the cutoff values. And the ADG test is also saying we can't reject the null hypothesis of non-stationarity, so we've got to do a lot of work on the Amazon data. The retail data set that we've looked at is kind of interesting because there's no real trend in this data. There's no non-constant variance per se, but we do have seasonality. And if we look at our ACF, I think the ACF is kind of interesting because there's a very strong autocorrelation for 12 and also for 24, indicating what happened this month is correlated with what happened a year ago and what happened actually 2 years ago, 24 months ago. And that's typical of when you have a seasonal data set. This would not be stationary. If we look at the KPSS test, what we can see is that the test statistic is about 0.3, so we cannot reject the null hypothesis. Remember, the null hypothesis is stationarity, so we can't reject that. If we look at the ADG test, we cannot reject the null hypothesis of non-stationarity, even though it's a little bit borderline. So we call 0.12 a little borderline. But I think this is an interesting example because all we have is seasonality here. We don't have the other conditions of non-constant variance or a trend to trip us up. Let's go back to the course packet. I now want to give you a little more background on differencing. So we covered this in week 1, but we need to do a few more things with it. So let me first define first order differences, or if I just say I've differenced my data, what that means is I've done a first order difference. So that's why we don't usually use the term first order, but you could if you want to really emphasize that we're just looking at the difference between successive observations. We're going to put a little prime sign as a indication that this data have been differenced. That prime sign is reminiscent of a first derivative. A couple things to notice about this. We don't have a value y0, so I can't compute y1. Therefore, I only have t minus 1 values. The interpretation of this is it's simply the change between one observation and the next. So I like to think of this as the immediate trend. So what is the trend that I've just observed? And that's very much like what we were doing with the Holt method. So the Holt method was computing that most recent change or most recent difference and giving it weight beta, and then giving weight 1 minus beta to previous changes that we'd seen. I'll just mention my lecture on the random walk model with drift. You should probably watch that again unless you really understood it, because we assumed a very specific model and showed that this differencing removed the trend and also removed the heteroscedasticity. So that was a very important lecture kind of leading up to this video. We also talked about second order differences. So second order difference we're going to indicate by the double prime. It's simply the difference between the differences. So we're going to take the difference between the first order differences, and that gives us the second order difference. Well, we can do a little bit of algebra, so go plug in what the y prime t is, go plug in what y prime t minus 1 is, and this gives us an expression for that second order difference. So in this case, there's only going to be t minus 2 values, since both y double prime 1 and y double prime 2 are not defined. We can interpret this as the change in the immediate trend. Remember, first order differences tell us what's the trend now. Well, this is just trying to say, how is that immediate trend changing? It's analogous to a second derivative. So second derivatives are continuous. Here we have discrete time, and so that's why it's just an analogy, but it plays the same role of the second derivative. It's going to tell us the curvature. We could go on to third order, fourth order differences, and so forth, but in practice, usually that's not needed. The last type of differencing that I want to talk about is called a seasonal difference. So the seasonal difference means I subtract the current observation from what happened last year. So this is August. I would take whatever happened this August minus what happened last August to give me the seasonal difference. We're only going to have this for t minus m values, where m is going to be the number of seasons that we have. So if it's annual data, we would have 12 seasons, or 12 months. That's a better term for it. But in general, since it's the seasonality, we call them seasons, even if it's a month or a day or whatever that unit is. And the interpretation of this difference is it's just the change between one year and the next. Well, let's go take a look at the Amazon data. So you've got my code. I'm going to go back to R and do this live. If we look at the Amazon data, we concluded earlier that there were a ton of problems. I'm first going to address the non-constant variance. So notice the spread's getting bigger by taking a Box-Cox transformation. So I've just made a new data set, BC Amazon for Box-Cox Amazon. And so what we see is that the variance has been improved through that transformation. If I do an augmented Dickey-Fuller test, what we're going to see is that I still can't reject the null hypothesis of non-stationarity. We've still got work to do. That should have been obvious from the plot, where clearly there's a trend and clearly there's seasonality. So we've got some work to do on this. So the next thing that I'm going to do is take seasonal differences. So this is kind of important. I'm going to go over this on the next slide as well, but we usually address seasonality first. Let's go take differences with a lag of 4. So that means this is quarterly data. If this is fourth quarter, subtract this period from last year's fourth quarter. If I go look at the auto plot, this is looking a lot better. Maybe there's a little bit of a trend, but I don't see, I'm not sure I've got any regular seasonality at this point. So that seasonal differencing will fix a lot of things. If I look at the ACF indicates I've still got some problems. So first ACF coefficient is very large, signaling I've got some work to do. If we look at the KPSS test, what we can see is that the p-value is borderline, so we would reject it at the 5% level, but not at the 2.5% level. So it's kind of borderline. If we do the Dickey-Fuller test, we come to the same conclusion. So it's a borderline significant result. We maybe have stationary data. So at the 0.05 level, we would reject the null hypothesis and conclude stationarity. But at a higher confidence level, say 1%, we wouldn't be able to reject it, suggesting that it's not completely stationary. Perhaps we could help it by taking first order differences. So here's a command that will take the seasonal differences and then compute first order differences to get rid of that trend that I think we were seeing. Let's go take a look at it, and now I think I have white noise. I don't see any trend, I don't see any seasonality. There's not much left in this time series. If I go look at my ACF, I have a couple that are borderline significant, but it falls off very quickly. I don't think I have stationarity anymore. If we look at the KPSS test, the test statistic is tiny. We can't reject the null hypothesis of stationarity at any of these levels. Likewise, the Dickey-Fuller test is saying you've got stationary data. So the p-value is tiny, reject the null, go with stationarity. One thing that I hinted at in this, but this deserves a separate slide, is when you have to do seasonal and first order differences. So you've got seasonal data and there's a trend, it doesn't matter which one you do first. So my algebra here is meant to convey that those two are exactly the same. So let's write this out. The seasonal difference at time t minus the seasonal difference at time t minus 1. This is going to be yt minus yt minus m, where m is the number of periods that I have. And this is going to be yt minus 1 minus yt minus 1 minus m. Now, I'm going to rearrange a few things here. I'm going to rewrite this as y sub t. Let me just draw arrows to show you where this stuff is coming from. Minus yt minus 1. The minus goes in front. And then what we're going to do here is I've got a negative. I'm going to pull that out. Y t minus m. And then you've got a negative and a negative, which becomes a positive. But there's a negative here, so 3 negatives make a negative. Y t minus 1 minus m. So let me just write where all this stuff is coming from. What we have here, though, is this is just y prime t minus, well, what do we have here? This is y prime t minus m. So the point I'm trying to make is, if we were to take first order differences first and then compute the seasonal difference, that's the exact same thing as if I were to take the seasonal differences first and then do first order differences. So algebraically, it doesn't matter if you do seasonal differences first or first order differences first. You'll get the same answer. With that said, we usually do seasonal differencing first because what often happens is when you've done your seasonal differences, you end up with a stationary data set and there's no need for first order differences. Let me just kind of put one little caveat on that. That assumes that you've got seasonal data. If you don't have seasonal data, you don't have any business computing seasonal differences. But when you do have seasonal data, compute seasonal differences first, go look at it exactly the way we did with the Amazon data. If there's more to explain, then go do your first order differences. It's been a long video. I want to cover one more topic, which is something called the Backshift operator. So the Backshift operator is going to be a very convenient way for us to express that we've differenced something. So big B operated on yt means the previous observation, yt minus 1. If I took big B times y operated on yt, that gives me yt minus 1. And if I apply b again to yt minus 1, I get t minus 2. The notation that we'll use is b squared operated on yt gives us 2 periods back. In general, if we want to shift something back m periods, if I want to compare this August with last August, I would use b to the 12th power if I have monthly data, b to the 4th power if I have quarterly data. I want to go over a few more situations. So how do we express a first order difference using this Backshift operator? Well, remember what the first order difference is. We're going to take just the current value minus the previous value. But using the Backshift notation, that would be yt minus b times yt, or b operated on yt. And we can factor that out as we would with normal algebra. So if you take 1 minus b times yt, what that means is we've done a first order difference. Likewise, a second order difference would be 2 of these. So 1 minus b squared. So let's just try to write this out. 1 minus b squared yt is going to be 1 minus, this is going to be 2b plus b squared yt. And this is equal to yt minus 2b yt plus b squared yt. So this is yt minus, this is going to be 2 times yt minus 1. So this whole thing evaluates to yt minus 1. This is going to be plus yt minus 2. So that in the exponent means go 2 back. But we can see that this was just y prime t minus y prime t minus 1, otherwise known as y prime prime sub t. And so that's the way we can write a second order difference. What about a seasonal difference? Well, a seasonal difference is simply go back m periods. So this would be yt minus y t minus m. And so this is the way we would write a seasonal difference. If we wanted to do some sort of a combination between first order difference and a seasonal difference, this is the way we would write it. So let's go over to the document camera, and what I'd like to do is work this out. So this is going to be 1, so multiply this times this, and then minus b to the m. Then if we start doing the top here, minus b, and then this times this is going to be plus b to the m plus 1 yt. So this works out to be yt minus b to the m yt minus yt b times yt plus b m plus 1 yt. So this is equal to yt, then this says go back m periods, so minus y t minus m minus y t minus 1, and then this is going to be plus y t minus m minus 1. And what I'd like you to note is that that is exactly what we had up here. So those two are equal. Let me just write it as that means equal. So we've got this term, we've got a minus yt minus 1. Here's this. And so my claim is that what I've just shown is that this notation is the way we can write whenever we have a seasonal difference and a first order difference. Let me summarize the key points in this lecture. So first, we're going to use something called an autoregressive moving average, or ARIMA model, to model autocorrelations between the observations. But in order to do so, we've got to have a stationary data set. There are several ways that we can identify a non-stationary data set. So we can use the time plot, we can use our ACF, we can use some of the unit root tests. If our diagnostic suggests that we've got non-stationarity, what we do is we use Box-Cox to address non-constant variance, and some combination of differencing to remove the seasonal and the trend effects. And then, having done that, we can fit our ARIMA model. In my next video, we'll start tackling ARIMA models.